So good morning. Welcome to Mass 206, Abstract Algebra 2. So this is a continuation of our discussion. We have already talked about Lagrange's theorem in the last lecture. If you can recall, we state the Lagrange's theorem as a result on a finite groups. We state that in every finite group, the order of a subgroup is a divisor of the order of the group. One of the remarks we make about the Lagrange's theorem is that the converse is not generally true. The converse is to say that if a number is a divisor of the order of the group, then there will be a subgroup whose order will be equal to that number. So this statement is not generally true. I think today we are going to start by providing a counterexample to this statement, the converse of the Lagrange's theorem. So a counterexample to the converse of Lagrange's theorem. Good morning, sir. So we are going to look into the symmetry group. You can still remember what symmetry group is. It is a group of permutations on n symbols. So we look into S4. So let us consider the alternating group. Alternating group A4 on 1, 2, 3, 4. That is group of all even permutations on 4 objects. You can write them as 1, 2, 3, 4. So an alternating group of degree 4. You can say of degree 4. We know that the order of A4 is 4 factorial all over 2, because all in the symmetry group on 4 elements you have 4 factorial elements, but then 4 factorial all over 2 will give you the order of the alternating group. That is, there are exactly half number of even permutations, and that number will be 12. So this is a group of order 12. In fact, we can list all the elements. In fact, we can see that A4 consists of this element, the identity. The identity is a number in A4 because this is an even permutation. Now, a cycle of odd length will always turn out to be an even permutation. Well, roughly speaking, we define an even permutation to be a permutation that can be expressed as a product of even number of transpositions. So, such as identity permutation is an even permutation, and you can think of the product of 2 transpositions because 3, 4. If you take a transposition, it's not an even permutation because it is a cycle of even length. A cycle of even length is an odd permutation, and a cycle of odd length is an even permutation. And then, so if you have odd and odd multiply together, you get even. So this is an odd as a permutation, and this is odd permutation. If you compose the two, you get an even permutation. So a product of 2 transposition will always be an even permutation, and you can have all of them because these are self-inverses. So you can have 1, 3 and 2, 4. You can also have 1, 4 and 2, 3. These are the 3 even permutations existing in 3 product of 2 transpositions in symmetry group S4. And then the odd length cycles 1, 2, 3. That is cycles of length 3. This one will be an even permutation, and then you have its inverse will be 1, 3, 2. Then you have 1, 3, 4. And the inverse of this will be 1, 4, 3. The next one would be 1, 2, 3, 4 with inverse. I think 1, 4, 3, 1, 2, 4. I have now written 1, 2, 4, and then 1, 4, 2. And then we have 2, 3, 4, and 2, 4, 3. So if you look at the number, we have 12 of them. And that's the order of the alternating group. This is A4. So the order of the alternating group is 12, and we have 12 of them. And if you look at this 12 elements, they are of three kinds. We have the one cycle, which is the identity, and we have three product of two transpositions. Okay, we have three product of two transpositions, which are also even permutations, and then we have this group. These are the three cycles, and these three cycles, there are 8 of them. We have 8 of them. So we have 1, 3, and 8. This gives us 12 elements. So 3 kind of elements. So if we are to have a subgroup of this group, this is the group we are looking at as our group G of order 12. And the converse to Lagrange's theorem, if it is to be true, it is saying that corresponding to every divisor of 12, we must have a subgroup of order that divisor. But now we are going to see that 6 is a divisor of 12. But there is no subgroup of order 12 in here. So for if a subgroup H of A4 is to have order 6, then that subgroup must contain H must contain the identity. Identity must be there, and at least one product of two transpositions and at least one three cycle. Sorry, at least one 3 cycle must be there. So why am I making this claim? The reason is that if you are to have a subgroup of order 6, every subgroup must contain identity, so the identity must be there. And if you want to form the subgroup using exclusively all the 3 cycles, this will not be possible, because if you remove identity out of the 6 element, you'll be left with 12 element. And so you cannot form the remaining, you will be left with, not 12, 5 elements. So if you remove 1 out of 6, you have what? 5 elements. And the remaining 5 elements in H cannot be formed using the 3 cycles, because the 3 cycles, they must come in pairs. If you pick 1, 2, 3, you must pick its inverse, because in a subgroup, every element must have its own inverse inside that subgroup. Are you following? So therefore, it means if I pick any one, I must pick its inverse. And if you pick this, you also must pick its inverse. So, and that is 4 so far. And then if you pick the last one, you also must take its inverse. And that will be up to 6. So they are coming in pairs, so they cannot account for the remaining odd number, 5 elements. So which means you have to pick from here and also pick from the product of two transpositions. And this product of two transpositions, there are only 3 of them. They are not up to 5. So if you take the identity and the 3 product of two transpositions, you must take what? Something, some element from the cycles of length 3. So which means a subgroup of order 6 must contain the identity and a product of two transposition, and it must also contain a cycle of length 3. So all the 3 kind of types of element that are in A4 must be present in this subgroup. So if we assume now, if we assume that this one, that is, we pick 1, 2, you can take any one of them, it doesn't matter. 1, 2, 3, 4, and 1, 2, 3 are in H. So if you take this to be in H, then what will happen? H must be closed because it's a subgroup. So if you assume this is the cycle in, this is a product of two transposition in H, and this is the cycle of length 3 in H, then H must be closed. It means the composite of the two must be in H. So you must have this composite. One, 2, 3, 4, composite 1, 2, 3, which is equal to, so if you do this composition, 1 is mapping to 2, and 2 is to 3, it means 1 will map to 3, because this is how we read cycle notation. And then you have 3 is mapping to 4 here, and 4 is fixed because it is not there. So you have this element, 1, 3, 4, and it must be in H. But then if 1, 3, 4 is in H, and H is to be a subgroup, the inverse of this must also be in H. And so also the inverse, 1, 3, 4 inverse, which is equal to 1, 4, 3, must be in H. And again, by the closure in H, you must have 1, 2, 3, 4 composite 1, 4, 3 to be in H. This composite is equal to, it's giving us again another cycle of length 3. So it is 1 to 2, and 2 is to 2 over here. 2 is mapping to 1, and 1 to 4. This is what is going to happen, because 4 is to 3, and 3 to 1. So this cycle is closed. So you have this cycle, a cycle of length 3, again in 4. From which we must have the inverse of this, 1, 2, 4, 1, 2, 4 inverse, which is equal to 1, 4, 2, to still be in H. So the inverse must also be in H. And if you continue like this, you see that again you can still find more elements, because the composition, the closure is still implying that if you take this inverse and multiply with this, you still end up inside H. So if I if I multiply 1, 2, 3, 4, which was already assumed to be in H, with this new element we have in H, we still have to get an element in H, which is now 1 is mapping to 2, and 2 to 1, so 1 would be fixed, 2 to 1, and 1 to 4, 4 is to 3, and 3 to 3 over here. So this will still be in H. And its presence in H will now force the inverse to still come in H. But I think we are already exhausting almost all the elements in the group, because we have this element was in H, taken to be in H, and this is in H. So 2 elements, and you have the third one, the fourth element, the fifth element, the sixth element, the seventh element. This is already beyond the order. Are you following? You remember the order was 6. So therefore, it means if any subgroup of order 6 is to exist, it must to have the 3 type of the element must exist in it, and then once that happens, you will eventually see that the order must be bigger than 6, because it's a contradiction. We assume the order is 6 and we are getting more than 6. So this is already a contradiction, which means right from the beginning that subgroup was not having order equal to 6. The order cannot be equal to 6. So therefore, and it is the same even if you take, it doesn't matter whichever choice you started with for the product of 2 transposition, because somebody may say, what if instead of taking this one, I assume it is one of the other 3, the other, because there are 3 of them. So if it is one of the other 2 product of 2 transposition, and you took something else apart from this choice, even if you take a different cycle of length 3, you can still analyze it in this way and end up having more than 6 elements. And so therefore, there can be no subgroup of A4 of order 6. So thus, since we already arrive at more than 6 elements, thus there is no subgroup. There is no subgroup of A4 of having order 6, and hence, so the conclusion of this is to say that the converse to Lagrange's theorem is not generally true. The converse to Lagrange's theorem is not generally true. So, well, not generally true. Not generally, because you can have subgroups where corresponding to every divisor there is you can have groups where corresponding to every divisor for the order of the group there is a subgroup. For example, we will see later that if the group is of prime power order, then corresponding to every divisor, because all the divisors will be also powers of prime, so there will be a subgroup. This will be an issue for a later discussion. We are going to prove results that will address converse to this Lagrange's partial converse to the Lagrange's theorem, and this would be the Cauchy theorem for finite groups, and then we'll also talk about later on Silo theorem, which is also addressing the converse, because Silo theorem is saying if the divisor is a power of some prime, then you will definitely have a subgroup having that divisor as its order. Okay, so to continue talking about subgroups, we extend the definition of coset to cover subset, not necessarily a subgroup with a singleton. So we recall that the coset of H, now a subgroup H in G generated by an element A in G is this set. And here we can talk about right coset. Right coset. So it's this set HA, which is the set of all HA such that H is in H. So we can extend this to cover subset, not general, not necessarily coset or subgroup in general. So for example, in general, if H and K are subgroups of the group G. So G is always a group for us. Then we can define product of H and K by HK product. So it will be the set of all HK such that H is in H and K is in K. You see, if K is to be singleton containing A, then you have this. If you replace this with a singleton containing A, then you have this. But we are assuming here that both H and K are subgroups. So you can multiply subgroups to produce a new subset of the group. For example, let me give you an example. For example, if H is a subgroup 1, 1, 2, and K, I take 1, 1, 3, like subgroups of S3. S3 being the symmetry group on 3 symbols. Then the product HK is equal to, so you multiply this element, you multiply the H and K element wise, so that you say identity, and this is the identity coming from, but they are the same identities. So 1, 1, 3, 1, 2, 1, 1, 2, and 1, 3. And this would be 1, 1, 3, because if you are multiplying with identity, you just get the element back. And this is 1, 2. Again, 1 is the identity. You can perform the product here. For permutation, 1 is mapped to 2, and 2 is mapped to 2 because it is fixed over there. So 1 to 2, and 2 to 1, 1 to 3 here. So you have this cycle. So this is the resulting product. And also, KH. If you do KH, you still get 1, 1, 1, 2, 1, 3 times 1, and 1, 3 times 1, 2. And this is equal to 1 as in identity permutation, and then 1, 2. Then you have 1, 3. Then 1 is mapped to 3, and 3 over here to 3. 3 to 1, 1 to 2. So this is the permutation. But if you look at these two, they are not the same. So HK is not always equal to KH. This product of two subgroups is not commutative. This is what we are saying. But now the question I want to ask is HK a subgroup? Having learned Lagrange's theorem, you can conclude that it is not a subgroup. Why? Because if you look at the order here, you have 4 elements, and the main group is consisting of 6 elements. And Lagrange's theorem says what? That the order of a subgroup must divide the order of the group. So if you have any subset whose order is not a divisor of the order of the group, you can conclude that the subset is not a subgroup. So even though this is a subset of S3, since the number of elements in this subset is not a divisor, because you have how many elements here? 4 elements, and 4 is not a divisor of 6. So you will conclude that by Lagrange's theorem, both HK and KH are not subgroups. of the group S3. So it immediately follows from by Lagrange's theorem that HK and KH are not subgroups of the group S3. Well, this is good because we establish something, or we have a tool we can use to test whether a certain subset is a subgroup or not. Or otherwise, you can check the properties. You can inspect inside here and see that the inverse of this element is 132, and it is not inside, so immediately you can see that it's not a subgroup. Likewise, here the inverse is not there, and so on and so forth. And for example, closure does not hold here, because if you multiply 1, 3 with 1, 2, it gives you 1, 3, 2, and it's not there. You can do that, but there is nothing wrong with quoting Lagrange's theorem, since we have learned it, and then you can just make use of whatever you learn to progress in the theory. So this is it. Now, so we take two subgroups and multiply together from the internal version of multiplication. And then we now saw that for this kind of subgroup, the product is not a subgroup. But is it generally true that whenever you multiply two subgroups, the result is still not a subgroup? This is not generally true. There are situations when product of two subgroups will still be a subgroups. And then it will be good to know what is the condition attached to that situation. That is what will be the necessary and sufficient condition for product of two subgroup HK to be a subgroup. And this will be the content of this next result. So we have a theorem. Say let HK and H and K be subgroups of a group G, of a group G. And okay, then HK is a subgroup of G if and only if, this is a biconditional, it's a necessary and sufficient condition. And the condition is that HK is equal to KH. So immediately we see that here, this is not a subgroup, and the reason is because the product was not commutative. When we compute KH, it doesn't turn out to be equal to HK. And that is why the subgroup HK is not a group. So this is the condition. So actually, if it were the case that HK equal to KH, then the product HK will turn out to be a subgroup. And this is what the theorem is saying. So we can prove this result. It will not be a difficult result to prove. Let me do that here. Okay. So when we say something is necessary and sufficient, it means it's a biconditional. It's a two-way statement. You assume HK is a subgroup and prove that this is the case. And you also assume this is the case and prove that HK is a subgroup. So we can do it whichever way. So maybe we do it, we start by assuming HK is a subgroup and prove that the product here is commutative, that HK is equal to KH. So proof. So suppose HK is a subgroup of G. Then if X is in KH, if you take X in KH, I think I should say let H be. And let X be in KH, an element of KH. Then X would be equal to HK will be equal to KH for some K in K and H in H. Yeah, because that is what it means to be in KH. All elements here are product of some element in K and some element in what? In H. And so this X, we can write it as KH, the inverse of the inverse. So this is KH inverse, inverse, and still inverse. Is that okay? Which would be equal to, but I can apply the inversion law. You can, if you take the inverse of a product, is the product of inverses, a reverse order. So it's H inverse, K inverse, inverse of that. Is this okay? Yeah, I think it's okay. But H inverse is an element in H because H is in H and H was a subgroup already. And K inverse is also an element in K. So therefore, this product will be in HK. But we already assume this HK is a subgroup of G. And so therefore, the inverse of every element in here, such as H inverse, K inverse is an element here, its inverse will be still inside HK. So this is an element in HK. So thus, so what do we get? We took an arbitrary element of KH and it ended up in HK. So therefore, every element in KH is an element in HK, meaning KH is a subset of HK. So thus what we have is KH is a subset of HK. I'll call this one. Now, the other inclusion, because we are trying to establish equality of these two, they are set. So if you show this, it is contained in this and the other way around, then you have established the equality. Okay? So for all x in HK, since HK is a group by assumption, HK is a group. Where is it? Over here. We already assume it is a group. So the inverse, X inverse, will still be in HK. Okay? And so that inverse, X inverse, is equal to some H times K for some what? H in H and K in K. Is this okay? It's a subgroup, not a group. It's a subgroup. Thank you. Since HK is a subgroup, if you take any element from HK, its inverse is still in HK. And that inverse can now be written as some element in H and some element in K. Is that okay? And so this is it. And so X, which is equal to X inverse, can be written as HK inverse, which is equal to K inverse H inverse. And now K inverse H inverse is an element in KH. This is where we want to arrive at. Is this okay? So this is the approach. So we took an arbitrary element now. Every element you pick, it will end up being in KH. So that it means HK is a subset of KH. Call this equation 2. And then from by 1 and 2, equality happen. Okay? So hence, by 1 and 2, we have HK equal to KH. So this is one way. Conversely, if we assume HK equal to KH, we can still achieve having HK being a subgroup. So we can prove the converse now. So conversely, if HK is equal to KH, then for all XY in HK, okay, we can, maybe I'll put it like this. Suppose HK equal to this. And let XY be in HK. So we want to show that HK is closed under what? The binary operation. So if it is closed under the binary operation, we also show that it's closed under inverse. These are the conditions, necessary and sufficient condition. You know, clearly you can, it's justified that HK is not empty because these are subgroups. At least identity is there. Okay? So if you take this, then X is equal to H1 or HK, H1 K1, and Y would be equal to H2 K2 for some H1 H2 in H and K1 K2 in K. Yeah, because this is the nature of element coming from here. Is this okay? But then if you take the composite, the product XY, this would be equal to H1 K1 times H2 K2, which is equal to H1 K1 H2 K2. By associativity, I can move the brackets around. But this product is in KH, and KH is equal to HK. So I can still write this product as a product of elements in one from H and the other from K. Okay. Now, but this can be written as H1, H3, K3, K2, where I took K1 and H2 to be equal to H3, K3, since this is an element in HK. You know, because this element H1, K1, H2 is an element in KH, but KH is equal to HK. So every element here can also be written as some element in H and some element in K. So so this is what I did now. So I write this as that because of our assumption over here. So this is why we use the assumption. And then we have So therefore it means xy is equal to h1 h2 and not h2 h3 and k3 k1 k2, but this is an element in h and this is an element in k, so this will be in hk, so meaning hk is closed under binary operation. Okay, also x, which is equal to x inverse, it will be h1 k1 inverse, but that will be k1 inverse h1 inverse, but k1 inverse h1 inverse would be what? An element in kh, but that is hk by assumption, and so therefore it is inside hk, which means hk is closed under multiplication. It is also closed under taking inverse, hence hk is a subgroup. All right, so this is as proved the theorem. This is the proof of the theorem. So with this, I think there is an immediate corollary to this one, to this theorem. And the corollary is to say that if you are in a commutative group, abelian group, then always product of two subgroup will be a subgroup. Why? Why is that so? Yeah, because if you are in a commutative, if H and K are subgroup of a commutative group, abelian group, then this condition will always hold. The condition is always satisfied. So in a commutative group, so if G is abelian, then for any two subgroups whatsoever, because the condition will always be true, H and K, HK is a subgroup of G. You always have HK to be a subgroup of G. So for any two subgroups, and there's nothing to prove there because we have it's clear that the condition is automatically satisfying. You may want to ask this subgroup or the subset in general, how many elements are there in the subset? But if that is, if H and K are subgroup of a group, HK may not necessarily be a subgroup, but then the order may be of special interest. That is in the situation where G is finite. So if G is finite, what will be the order? It's already a theorem that this order can be calculated by the order of H and the order of K, and also the order of the intersection. So if G is finite, G doesn't have to be finite, it can be infinite, but so long as the subgroups are finite. So if H and K are finite subgroups, of finite subgroups of G, of a group G, then the number of elements in HK will be equal to the order of H times the order of K divided by the order of H intersection K. I don't know whether you you can still remember what this is. That you can still recall that the intersection is always a subgroup. Intersection of two subgroups is always a subgroup. So you can speak of the order of the intersection. Okay? And so, the theorem is not difficult to prove, but a bit tricky. So how do you just count the duplicates? You know, it's like the order of H is how many elements, the number of elements in H, cardinality of H, and the order of K is also cardinality of K and the cardinality of the intersection. So maybe you can just look at when you do the counting, how many duplicates are there in the products? Because if you look at the row, the element in HK, I'll just give you the way to prove this thing. If you look at the element in HK, this is H times K, such that H is in H and what? K is in K. But you can see now here that how many such pairs do you have? It's exactly order of H times order of K. You will have as many such pairs as if you are talking about pairing the element. But then when you multiply out H times K, there may be a situation where the product will be the same. You know, what I'm saying is sometimes you can multiply H1 and K1 and then it will be the same thing as H2 and K2. So some pairs, there may be some duplicates in the counting. So how many such duplicates are there? That is what you need to count, because if you know how many duplicates are there, you can just you divide by the number of duplicates. Okay? So, and the theorem is suggesting that there are as many duplicates as the number of points in the intersection, the element in the intersection. And so you can do that by looking at the intersection. So if you pick any element from the intersection, so first of all, we see that if we take any element x from the intersection, x is an element of H intersection K, then for all, we see that for all, in fact, because this is happening for all elements in the intersection and all H in H and K in K, the product, you can always write HK to be equal to H X X inverse K. This can always be written like this. So which means, and this element is in H because X is in H, since it is coming from the intersection. And also, this is in K because X inverse is in K because it comes from the intersection. You know, this intersection is already a subgroup. It's already a subgroup. And so therefore, this is happening. So, which means every element of the intersection is giving rise to a duplicate. Are you following? So this is telling us that there are the number of duplicates involved in this product is at least the number of points in the intersection. Okay? So therefore, this equation So thus it means the order is always less than or equal to the number of duplicates. So it will be number of duplicates in HK. This is what we arrive at. And on the other hand, if we take a duplicate in here, that is, if we take HK to be equal to H1K1, then to be a common element, maybe let's say Y, then it will follow that, okay, no, sorry. If we have a duplicate, then because you can see that H1 inverse or H1 inverse H is equal to, I will cancel K from this, K1, K inverse. I think this is the right thing. We do left cancellation for the H1 and the right cancellation for the K. So that we'll cancel K from here and we'll also cancel H1 from here. So this element is equal to Y will be an element in H and at the same time element in K, because this is an element in H and also it's an element in K. Okay, so which means it is an element from the intersection. So every duplicate is giving rise to an element in the intersection. What is this telling us? That the number of duplicates is at least the number of duplicates is less than or equal to the number of elements in the intersection. So therefore, the number of duplicates in HK is less than or equal to the order as many elements as there are in the intersection. So it's the order of H intersection K. So this is it. But then, if you look at the two inequalities, it means equality happen. So from the two inequalities, you have exactly this number of the duplicates in the counting of elements. So hence, so it's just a simple counting principle, but a little bit tricky. So the number of elements in HK would be equal to the number of elements in H times the number of elements in K. This is understood. But what if there are duplications in the counting, because maybe element may repeat in there? We have taken care of all those duplications. We found the number, and it is what? Order of H intersection order of K, intersection K. And that is it. This is the claim of the theorem. Okay? So we have a way of doing the counting. You know, finding how many elements are in this subset. May not be a subgroup, but always a subset. Okay? Yeah. So I think the next thing to talk about is normal subgroups. You remember in one of our examples, the cosets we obtain for one subgroup, all the right cosets coincide with the left cosets. But then for the other subgroup, the right cosets are not the same as the left coset. So for some subgroup, left and right coset are the same. There is no distinction between left and right coset. For such type of those are the kind of subgroups that actually we call normal subgroups, and they will form the topic of the discussion in our next lecture. I think this is a good point to stop. Thank you very much.